Okay, so I mean, I changed the topic of the talk because I think it's much more appropriate for here. I mean, I think it's clear to everyone that you know, the tool in machine learning, in particular deep learning, like neural nets, have completely changed the landscape of our daily life, actually, over the last decade. I mean, you know, a decade ago, many problems in speech or image recognition were actually, you know, active topic of research. They still are, but it was not clear at all, or one would proceed about doing any of that. And nowadays, I mean, your phone can do these things fairly easily. Okay, and the big breakthrough was, you know, the use of these deep neural nets, which were combined with, you know, big machines, computers, to actually train them. And so I'd like to discuss, you know, a little bit what this is about, because one of the questions is really, I think, and remains fairly open, is why do they work so well? Okay, and so at some level, you can think about the fact that one possible explanation for this is the fact that these neural nets are actually fairly efficient at representing accurately high-dimensional functions. So you see what you see here, for example, is the NIST data set of the handwriting, right? And so what you can think about is that, well, you can think about this as, you know, if you pixelize these images, right, what you're trying to learn essentially is a function that takes the value of the pixel, so it takes 0, 1 to the n squared, so it's a fairly big domain of definition for the function, and then maps them into, you know, 0 to 9, right, and try to do that in a way which is efficient, and you give some training set, and then you learn the function, and then you can use it on any data set you have. In principle, it will recognize the numbers, and this is what's actually happening. So if this is really happening in that way, and you can learn function in high dimension, well, not only, you know, it opens enormous possibility in machine learning and computer science, but also for applied mathematics and computational mathematics. I'm an applied mathematician, because any calculation that you do start with a presentation of a function. Like typically, if you want to do anything on the computer, I mean, you need to represent it. And we have been told that there is something which is called the curse of dimensionality, which means that you can't quite do that. You want to solve a PDE, right? The standard, you know, the common knowledge will be to tell you, well, you can do that in 2, 3 dimensions. You can use sparse grid and maybe go a little bit higher if there is some special structure. But if you were to say, I'm going to solve a PDE in 20 dimensions, people would tell you, you can't do that. It's just not possible, okay? And, well, that seems to maybe not be completely true at the end of the day. It could be that something is actually changing here, which is that, in fact, we all thought that, but at the end, maybe not. And the reason is, in a nutshell, that's what I'm going to try to maybe, you know, explain a little bit more, is that, well, when we talk about standard representation that we use, like Galerkin truncation or Fourier basis or, you know, finite element, these representations are all linear representation. You make superposition, you take a basis set, you truncate, and then you superpose that. That means that the dimensionality of your representation is essentially the size of the truncation, and that's all there is. But when you look at neural networks, and I'll explain, you know, in which way I want to think about them later, well, they are highly nonlinear in their adjusting parameters, which means that the number of parameters that you have in the network is not the dimensionality that, you know, of the representation. Okay, but what I would like to do is to try. Can one explain these features somehow? Can we get a framework that explains that a little bit, and also would explain the fact that you can actually train them? Okay, but before I go to that, let me just show you something which, you know, to my mind, this is the way I started the project actually, and to my mind, this remains like something that is almost like magic. I mean, which is. So we took the 3-spin model, which is so it's a complex function defined on the high-dimensional sphere. Okay, so it's a polynomial in this case because 3-spin is just a cubic polynomial in X, where you have random coefficient and you restrict that to the sphere. Okay, this function is known. It's been studied by mathematicians like Gerard Benahous. It's known to be a highly complex function. In particular, it's known that the number of critical point minima, in particular, but grows exponentially with the dimensionality. So it's in no way a function that you can think can be represented, you know, as lying on a low manifold of some form. It's really something which is quite complicated, right? And then you take you take a neural net representation. I'll show you later what that is and which one we use. They are fairly simple, in which you essentially take only 128 up to 1,000 parameters, so nodes in the network, right? And you see that if you do representation in 10 or 25 dimension, right? I cannot show you, of course, the function on this, but I can take slides. You can look at great circles, right? You see that with as few of, these are fairly small number compared to considering the dimensionality, you get a signal. Like you slice this function, you look at it, and then you realize that in fact it's picking up. The yellow curve is the actual slice, right? And I mean they don't look very complicated, but you need to realize that they are different on every single slice, right? And you see that you clearly the function that you have here is an accurate representation, even in 25 dimensions. You lose a little bit of accuracy, but if you look at the one at 1025, it's actually following the features fairly well. And if you train the network longer or with a bit more parameters, you start to have accuracy not only in 25, but we pushed it to up to 100, and you still find a signal. That's totally remarkable. I mean, that's if you think about it, that's really like people tell you cannot fly, and then somebody build a plane, and suddenly something is different. I mean, there is something here. So I don't know, So I would like to understand what's going on here, because it looks a little bit like a mystery. Okay, so the way we're going to look at that, right, is first I need to define, what is an. I mean, because I'm going to look at neural networks in a bit of a different way than the one that is typically presented in machine learning, right? I'll really look at them as way to represent functions, okay? And the way you can think about them is like that, is that you say you have a function that's defined a domain, which is a subset of RD, and you want to represent it by this neural net, and what they do is essentially you take some form of kernel here that depends on parameters, and then you have weights, and you make a representation of this type. So it's a superposition of these kernels weighted, where you have adjusting parameters here. Okay, so many examples that come from machine learning can be cast into this form. For example, if you look at radial basis function network, well, that's a case in which the parameter here, the y's, lives on the same space as x, right? And you have a kernel which could be, for example, a Gaussian kernel like this. Okay, the standard single layer neural net is more something where you would take one-dimensional function h, for example, with a sigmoid nonlinearity like this one, and then you take a vector from which you multiply x, that's a, and you add a constant. Okay, so it's like a step that picks a direction and makes the step at a given place. And so and what you do is that here the parameters, so the y's are the a's and the b's that you adjust. Okay, and then deep neural network are just iterated version of that. Is that you take this guy into many directions and then you put it back into itself, like you iterate upon it. Okay, and the way so the way these parameters are being adjusted, like the c's and the y in this representation, is that you introduce what's called the loss function, and I apologize for people who really know about this already, just to fit the jargon, which is essentially, well, you look at the weighted L2 norm of the difference between f and fn, which is the representation, right? And so that will give you the quality of the approximation, and it will also give you a way to adjust the parameters. Okay. So as soon as you have this framework, then you can. Well, the next step is what are the questions? Well, there are obviously two main questions that naturally arise. Is that one is how good can the neural representation approximation be if you optimize the parameters? Right? Like, I mean, what's the scaling with n, for example, that you will get, and how does it depend on d, etc., etc. That's one thing. The second one is, I mean, is this trainable? I mean, this is an optimization problem that you need to do, and it's a complicated one a priori. So, is there any way? I mean, okay, there is something here which is like the best I can do. Can I actually do it? Can I train the network, right? And well, of course, from empirical evidence, right, from observation, shows that this is working very well, and that the networks are actually effectively trainable, right? But why is that kind of remarkable? Well, it's remarkable because if you think about it, if you put the representation in the loss function, which was this L2 norm, and then you just expand, what you end up having is an objective function of this type. So it's quadratic in the weight. That's okay. I mean, that would be easy to solve. But the y in there are, they come from the kernels because they are given in principle by the integral that are given here. So this is a fairly complicated objective function, right? Which is presumably not convex with many local minima, and is not completely clear, at all what the structure is and how you can actually do the optimization. Okay. There's another problem that one needs to address, and I'll get to that later, which is that, well, in principle, I mean, one cannot manipulate the function to the extent that you can actually calculate the loss function or these functions, right? Because typically what you have is you have a training set. So in this framework, what does that mean? Well, that means that the integral, the integral of the L2 norm needs to be approximated by a finite sample size, which is that you take points that are drawn from you, and then you just approximate the L2 norm by this sum, and that's the input that you have. Okay, so we'll get to that in a minute. For a while, I'll just keep going at this level. Okay, so how can one think about this problem and see that maybe it can be tractable? Well, we have seen a lot of that yesterday, actually. So here is a kind of a conceptual way that allows you to simplify the problem, which is to say, suppose that the c's and the y's that enter this representation are such that if I take the limit as n going to infinity, right, this sum can be represented as an integral over a sign density g. Okay. If you do that, well, if you say, well, that's it, I mean, in the same limit, which is as n goes to infinity, you realize right away that the loss function, it becomes actually quadratic in this sign density, right? So it means that by going from the space of these y's here to the functional space, which is of the density, you turn the loss function into a quadratic objective function for that g, okay? And in fact, this representation, I mean, this idea, it underlies many results that already exist in the literature. It's just putting that in a slightly different spin, which is to say that essentially, well, that's connecting. So if you look at what is the Lagrange equation for this, right, it's an integral equation of the first kind, Theorem equation. So there's a lot of theory that exists for that. It tells you in particular that giving any f in L2, there is another one that for which you can solve the equation that's arbitrarily closed in L2, for which you can solve. It's a weak, it's a weak solution actually that you get here, for which you can solve the equation, and that gives you a representation of the function. Okay, so it says that essentially you can pick any f in L2, you will be able to represent it to arbitrary accuracy with representation of this type. And obviously you can realize it, because if I give you what the G star is, this sign density, well, you could draw the y's from any density and then reweight it to get the C's. Okay, and that gives you a representation that guarantee by law of large number and central limit theorem that this guy will actually converge to the right f. Okay, so that's nice. But it's a bit of abstract nonsense in a way, because, of course, you don't know the G, right? And you can't quite work at this level. I mean, it's useful for abstract purposes, but of course, you don't want to solve this Friedel, the Lagrange equation I tell you is an integral equation of first kind. As you know, they are quite nasty. And it's one that lives in a very high dimensional space. You really don't want to do that way, right? You want to keep being at the level of the particles, the parameters. But still, it gives you a framework and a kind of an idea of what could be done. Okay, that's what we're going to do next. Okay, and so we want to go beyond that and try to understand the rate of conversion in time. Can we dynamically train the parameter to achieve this? What's the rate of conversion in time of this training? And what's the error due to the finiteness of it? Okay, so well, this is where I connect with the talk of yesterday, which is like the idea here is actually fairly simple, once you have thought about it this way, is we're going to think about the parameters as particles, and we're going to think about the loss function as an interacting potential. And then instead of looking at their level, we're going to make an analysis that involves the empirical density, okay, or empirical distribution, right? So I'll first do it with gradient descent, because that's simpler conceptually, and then we're going to go back to stochastic gradient descents in a minute, which is the one that use finite training set. So in the gradient descent, what you do is, okay, so you look at now the neural network representation as a dynamical function where you will learn the parameters, right? And then if you plug that in the loss function, you take the gradient, you take steepest descent, right, which is the gradient descent flow. What you get are these equations of motion for the particles, right? So the particles here are the y's and their c's. The c's are really like fractional charges, if you wish, for the particle, if you remember what was the form of the loss function. But you can think about them as particles themselves, right? So once you have done that, right, the standard trick now is to say, well, if you look at the empirical distribution, okay, which allows you to represent this function just, so if you test this empirical distribution against C phi, so where phi is the kernel, you get the representation of the function. And then, well, you can write down, it's essentially just chain rule, you can write down an equation for this distribution. And the equation is written here. You have seen it several times in the talk yesterday, right? It's just gradient descent over, well, the energy, which is now the functional equivalent of the loss function, which is written here, right? And where the gradient descent now is in the Wasserstein metric. That's the one that you have here, okay? And once you have written that and done this, well, you can then connect to many, many results from the literature of interacting particle systems, right? In particular, the result of Villani, Serfati. There's many, many, many people that have worked on that, which allows you to kind of try to understand what happened to the solution of this equation when n is large, okay? And in particular, I mean, there's two things that you can show, and I'll phrase them in a way which is convenient for the purpose that we have here. One is that you can take the mean field limit, which is the equivalent of a law of large number, which is that you can ask what happens if you take n going to infinity. Well, when n goes to infinity, you essentially can show that the distribution that you have converges to a solution of a PDE, so weak solution of the PDE, which you can, in this specific case, rewrite not by looking at the limit itself, which is the rho z, or the weak limit of that distribution. Instead of looking at that guy, you test it again. So you look really at what the f0 is, which is the zeroth order, if you wish, the dominant term in the expansion from the neural net representation. And you can write down an equation for it, which is the one here, where you see again that what it does is simply gradient descent on the loss function, right? This time there's a kernel which is given here, which is positive definite. Right? And then the term that is here is just the landscape has become quadratic because the loss function was quadratic to begin with. Right? This is just the gradient in the L2 mu, the weighted L2 norm of the loss function itself. Okay? And so you can summarize that in the following way, which is just kind of it's a rephrasing of the universal representation theorem that tells you that if you take these guys, right, if you take this representation, in which the parameters follow gradient descent that I wrote on the previous slides, then in the limit as n goes to infinity, this function converges to the solution of this integral equation here. And that one has the property that if you let t go to infinity, it converges to the actual f. Okay? And the reason why that's the case is because, I mean, again, this is you are now on a convex landscape. It's actually quadratic. There's only one minimum, and that minimum is the target function. So there's nothing else that can happen than actually going there. Okay? So that's one thing. So it's the universal representation term, except that it tells you in a way how you can realize it in practice. And it tells you one more thing, by the way, which is that since n has completely disappeared from this equation, it tells you also that the convergence in time here doesn't depend on the size of the network to leading order when n is large. Okay, this is an intrinsic property of this limiting dynamics that you have here. Okay, which is another interesting result about trainability. Now, of course, that doesn't give you the error. So if you want to go and look at the error, well, you can go and look at the fluctuations. You can try to prove a central limit there. Okay, and here it's a little bit complicated because if you think about the way you would prepare things, right, is that you need to initialize your parameters. So if you initialize the parameters, the best way you can do it, well, this is the other way. The standard way is done, not the best. The standard way would be done is that you pick the parameters at random independently for every I, right? You would pick a distribution and then you initialize. For example, you say I pick the C's, the weight to be Gaussian, and I pick the Y's to be uniform in their domain or with some prior. You take that and you take them all independently because you don't know what to do typically. That's the way people do it in practice. So if you do that, at the beginning of time, you know that the standard CLT tells you that the representation error will be of order 1 over square root of n. That's CLT scaling, okay? But you also know from these equations, Vlasov, etc., that in fact the scaling gets better as time goes on because the particle becomes a little bit correlated. You assume that they were initiated independently, but then they correlate their motion because they all feel one another. And so you can put that into, you can do that. And what you end up having is that what you can show, in fact, is that the scaling goes all the way to 1. So the error, right, that you get is that if you look at fn minus f0, right, the fn, which is the representation that you have, and the limit, right, they differ by something which is of order 1 over n, roughly. Okay, and that's what's being said here, right? That you can multiply this factor by n to a power which goes all the way to 1 and get 0 in the limit as you train the network. Okay, you can also, there's a difficulty here if you try to prove these things because if you do gradient descent flow, right, there is no stochasticity except from the initial conditions. So everything that you measure is with respect to the measure of the initial condition. You can get rid of that by introducing a little bit of noise in the equation to do, a variant of stochastic gradient descent that I will discuss in a minute, in which you put kind of, if you wish, you put a thermal noise over the equation. You do it, however, in a way which is such that you scale the noise by the number of particles, because if you do that, it guarantees that at leading order, the law of large number remains the same as before. And again, these things are very well known from the literature on interacting particle system, right? But then you can look at what happened at next order. In this case, you can actually prove a CLT where it's independent of the initial conditions, what happened at long time. And you can actually show that indeed, if you think about fn minus f0, right? Well, it's like 1 over n times a function which is a random function, which is a Gaussian field, okay, whose properties are specified here, right? So that's not the usual scaling that you would get for central limit theorem. It's better, because the typical scaling you would get for central limit theorem would be that you would have a square root of n here, not an n, right? But in this case, because of these, there's some self-averaging in these Vlasov systems that guarantee that this statement is true, okay? Okay, so all that is nice, but at this level, I've been working with the, this capital F and this capital K. And if you remember, these guys were obtained by making integrals, right? Which in principle you cannot do. So there's another aspect of the problem that needs to be addressed. Until when do I have? No.
I'd say 10 after.
Okay. So, okay. Okay.
Including questions.
Okay. Okay, keep that in mind. So there's another aspect that needs to be, is that if you want to do this calculation in practice, what you can hope is that you can evaluate your function f or your kernel pointwise in the physical space, but you will not be able to do these integrals. That would be asking for too much. And so what people actually use in practice, like to practitioners, machine learners, is that they use what's called stochastic gradient. And we have also seen that a little bit yesterday, at least in the poster. And so the idea is this, is that So what you do is that you approximate the integrals that give these factors by a sum over a training set, if you wish, of that type. But then you do something else, which is what I'm going to assume here, which is that if your training set is very large, you can actually redo that independently at every time step. So what you do is that you do a steepest descent, where these equations look like a discretized version of the gradient descent flow that I wrote before, discretized in time, right, like a Ford-Euler scheme, except that there is a twist, which is that I'm not using the real f, I'm using these approximations. Okay? And then what you do is that at each time you update the time, you recalculate these guys, right, on another training set. This is what's typically done in practice also. Okay, so if you think about what's going on here, right, and you know, this was Ben presented that last time, is that if you do this, it guarantees that in expectation, so if you take expectation over the training set, these guys, these here, give you the actual f, right, the real one, the f and the k, okay? And so you can think about these dynamics here as something in which you can rewrite the k and the f into the expectation plus a perturbation over it. And if you think about it this way, this starts to look like a discretization scheme like Euler-Maruyama for an SDE, okay? Except, so that's what's written here, except that there's a twist that, and in fact that's what helps in practice, that if you had, so if I were to decompose this guy into its expectation plus the noise above the fluctuation, right, I get like a discretization for an SDE, except that the scaling of the noise is wrong because I have a delta t and not a square root of delta t. Okay, but that's okay. I mean, you know, it doesn't matter. It still says that I can write down a limiting SDE here, right, where the noise amplitude that you have is just related to the delta t and the p, which is the size of the training set that I'm using, right? And you can what you can show is it's just a consequence of the fact that one is the Euler-Maruyama for the other. You can show that in fact this is an approximation of this. Okay, in the sense that, you know, if you look at any test function and you ask, well, you have the standard error that comes from Euler-Maruyama, the weak or the one error that you get from Euler-Maruyama that comes here, right? I didn't write for you what is the dB and the dB. These are white noise in time, except that they are correlated in space, because the noise that you get here is not additive. It's not like the one that I put by hand in the previous equation, right? The covariance structure of this noise is dictated by the covariance structure of all of these terms here. Right? It's essentially the covariance that you get if you take the expectation of this, right? Then you subtract these terms from these terms. You subtract the expectation. You look at the covariance of that. That's the covariance structure that you have here, in a nutshell. Okay. But so once you have understood that, well, what I'm going to do next is instead of analyzing this system, which is complicated, I analyze this one, which is also complicated but a little bit simpler because it's, you know, I can again look at the empirical distribution at this level. Okay? And so if you do that, well, you can do the same thing as before. So what I'll do here is I'm going to assume that either delta t or p is scaled in a way that depends on so that's the training set, the size of the training set. I'm going to assume that I can scale it with n, which is also what typically people do in practice, which is to say that depending on the size of the network, you take smaller time step, or more importantly, you increase the size of your training set. Okay? So if you do that, in fact, this is not really necessary for the equation I write here. It's necessary for the next step. Right? You can write down, formally at least, an equation for the empirical distribution of this equation, which is this SDE. Okay? And not surprisingly, you know, if you forget about the noise, it's the same as the gradient descent. So part of the term are the one that you would get from the gradient descent, and this is this line. But then you have additional term that comes about, and these terms are the terms that come from the noise structure that you have in the equation. Okay, and they've been scaled in a way. Here the theta has been scaled by that, so that's why now you see these scalings over here. Okay, and in particular, so this is the diffusive part that you get in the equation, right? It's come from the Ito term, if you wish, and that's the noise term that comes from with the structure which you see, which is from the noise that you had in the original equation. Okay. As a stochastic PDE, I can't say much about, that's certainly something that would have to be, I need Martin or Jonathan to look into these things. The noise actually being correlated, it's actually nicer than what you would get if you put independent noise on every particle, because in that case you get the spatial-temporal white noise, which is bad. This one is not of that nature. And yes?
Like question for me, but what's the correlation? What physically or algorithmically does the correlation tell you in the noise? Does it have meaning?
So I'm not sure I'm going to answer that question, but I'll answer something which is related, which is that you see that all of these guys here, I didn't write down for you what these coefficients are, but they are related. You need to remember that the deterministic part that you have in the equation, drift, right, is related to the gradient of the loss function, right? And the loss function is a quadratic function that goes to 0 as fn goes towards the target. Okay? And this structure persists here in the sense that if you think about correlation, all of these noises have a self-quenching property, which is the one that we also saw in the talk yesterday that was imposed, but here it comes for free, which means that if fn goes towards f, the amplitude of all of these A terms and of the noise quenches, goes to 0, in fact. Okay? And so this is the statement that is written here, which is that if you take any g, and in fact, if you evaluate that at 0, it's equal to 0. Right? And so you can use this property now to try to, again, look at what happened with these equations if you, again, try to do a law of large number and a CLT. The law of large number, at formal level at least, is exactly the same as before because these terms are all higher order. That's why I scaled. We scaled things in this way. Okay? So, but then the CLT is slightly changed, and what happened is actually not very surprising, right? Okay, so I'll write it here. It's a variant which is, so if you take same representation, right, and where this is the solution of the limiting SDE, it would be better if I were able to tell you something about the actual discrete system, but that's more complicated. There is one more step. What you can show is that if you scale this theta, which is, think about this as the size of the training set with n in this way, then you get a CLT again of this type, which is that the error quenches essentially all the way to alpha, right? And this is saying that so if alpha is less than 1, then the error that you come from the training set dominates. But if you push alpha all the way to 1, which is if you take that's the best training set that you can do. If you do more, if you take a bigger training set, in fact, it's wasteful. If you go all the way to there, then you get back to the error that you had essentially with the gradient descent, which is that then you get back to when alpha is equal to 1, is no longer that guy that makes the error, is the one that comes from the fact that at the end there is a discrete nature to your problem that you cannot avoid. Okay? And so you go back to that. So you get an error which tells you that if you scale your training set in this way, it gives that. And the best you can hope for is, but it's also the most costly, is to take alpha equal 1. So to take the training set like scaling like n squared, and then you go back to the optimal error that you had before. And again, I said that already. If you do more than that, if you take a bigger training set, it doesn't help because then you're wasting computational effort. Okay, so okay. So let me go back to this example. So let me explain to you a little bit better what the example is. Okay. So the representation of function is actually very simple. It's a polynomial, in this case a cubic polynomial because I'm going to take the tree spin, right? on the d-dimensional sphere, which is scaled in a specific way. This is all to do the calculation, more likely so the radius of the sphere is square root of d, which is the dimensionality. And then the coefficient that you pick here are independent Gaussian random variable with mean 0 and variance 1. Okay, so it's a random function, right? And as I told you that already at the beginning, if you look at this function, it has a number of critical points that grows exponentially with the dimensionality d in a way which in fact can be completely quantified. Right, because there's a mapping between this and random matrix theory that tells you precisely you can do all of the asymptotics of the number of critical point that you have in the function that's there. Okay, so to avoid confusion, let me tell you that this function has been used by people as an example of a function that would be like a loss function. This is not what I'm going to do. In other words, people have said, there have been analogies, right, with the loss function, saying it's like a glassy landscape with many local minima. So they try to analyze what would be going on using that as a loss function. I'm not using that as a loss function. I'm using that as a test function to represent with a neural net. Okay. And so what we're going to simply do here is we use our target function. And so what we take is that you pick specific realization of A, and then you train the network, increasing n in that specific realization, and you do that again and again to see what happens. Okay? And the first thing that is done is so this is like a picture representation, but if you were to do it in d equal 3. But okay, so if you take a Gaussian kernel representation, that's one which is actually easy because that's one in which that's one where the y's, the parameter, live in the same space as x again. So that's one where I don't need to do it. I can work with the gradient descent flow immediately. That's what's done here, right? And so what you see on the graph, I'm not going to spend too much time here, but it's just showing you how in 5 dimensions, so it's fairly low dimension, you can, so this is the scaling, this is the empirical loss. So what you do is that you train the network, okay, and then when it's been trained, you compute the loss function by Monte Carlo, because this is the only thing you can do in 5 dimensions, using a huge training set, and then you check the error and you see what happened when you increase the dimensionality, okay. And if you remember, for the gradient descent flow here, I was telling you that the statement says that the error needs to be less than n to the minus 1. I cannot tell you how much more. This is like an upper bound. It could be much better than that. I don't know. I know it cannot be worse. And that's indeed confirmed. This line is n to the minus 1. This line is n to the minus 2. Okay, so you see the error decreasing with n, and this is the type of representation that you get. Okay. Again, so it's a slice here again because it's a 5-dimensional sphere, right? So but you see that this is 128 points in 5 dimensions, and you look at the level set of this function, and they're essentially on top of one another. It's like this is too much. I've said already. There's something which is really remarkable in this, I think. Okay, these are the projection of the points, the center, the particles, right? I didn't insist upon that, but of course, if you think about gradient descent, right, the microscopic loss function, the one that is being seen by the particle, is indeed very rugged. There's many local minima. If you redo this calculation twice, these particles go at different places. Okay? In fact, if you put a little bit of noise on them, it's not even clear that it will converge. They will keep moving. Right? The convergence and the convexity of the landscape is not observed at the particle level. It's observed at the distributional level. Right? That's the one that converges and gives you the guarantee. If you insist on looking back again at what these particles are doing, and analyzing, am I at the local minimum, my global minimum, what's the estimate? It's extremely complicated what's going on here. It's only if you think about the empirical distribution that everything is nice and clean in a way. Okay? So that's that. Now, I have one more slide and I'm done. So this is the same thing, but using the standard. So this is really The previous one was done in MATLAB. This is using TensorFlow, using a standard one-layer single-layer network representation with a sigmoid nonlinearity of that type. Okay? And what you see here is, again, these are the functions that I showed you before, the representation. And here what you simply see is, so this is what you do. So this is the log of the empirical loss, okay, along the training in time, right, with the stochastic gradient descent. And as you see, it's actually not doing, it's not like getting stuck, or it's actually going down very nicely. It's, I don't know where's the ground truth, right? So it's at some point plateau. This little bit here is obtained at the end by quenching. So this is just to check the scaling of the noise that we predict, which is that if here, we had the training set was scaling with n, here is the optimal one scaling with n squared. So you train using a non-optimal n, if you wish, and then at the later stages, you just quench it to get the optimal one. Okay? And these scalings here are the predictions. So all of these lines are n to the minus 1. This is in 10 dimension. This is in 25 dimension. And you see the empirical loss again. This is what that is. And then just the function tested against something else just to see what is the error. And in each case, you see that the scaling, this n to the minus 1, is fairly well captured, observed in the data. Okay, so that's the error, right? And the corresponding functions are here. This is with the one that are there. Again, with not so many particles or parameters in the network. Okay, so I'm running out of time, and I see that the chairman is getting a little bit nervous. So what in a nutshell, what I said here, right? Well, I'm not going to repeat it, but if you look at this as a system of interacting particles, you can use all of the apparatus for interacting particles to analyze this system. And that gives you a framework to try to analyze it. And it shows you, in a way, that's one of the important messages, that this problem that looks extremely complicated because it's non-convex is in fact convex if you look at it from another viewpoint. And that may explain why these things are trainable, right? But on top of that, it also gives you something about the error. And it's quite remarkable that the error here doesn't depend on dimension. So you have beaten the curse of dimension. The n to the minus 1 is n to the minus 1, not n to the minus 1 over d, in a nutshell. Okay? And, well, if this is true, it really changes, and that's maybe the last, it really changes the way we can do computation now, because that means that in principle one can know, what you have been told to not solve PD in high dimension, well, perhaps should be revisited, because it looks like it could be doable after all. And I'll leave you with that.